Hey, good morning everyone. So let me know in the chat that you can see me and hear me well. Maybe there is some problem with microphone or something, so please let me know that everything is fine by typing in plus in the chat. And we'll start shortly. Just a second, looking some of the things. So can you see and hear well, plus, minus? Type please in the chat. Meanwhile, I'll check what is up with my screens, because I think it could be better. Anyway, okay, I hope this will be fine. So, okay, good. I see that somebody is responding with full sentence, so that's great. That's great. Okay, so we have today a really interesting topic. We have a template already up in the Google Classroom. So you can definitely try out already to download it and start getting it ready to use. Oh man. So, okay, I think hopefully that is there. So yeah, so please get template 6.2. And meanwhile, we will introduce this topic. So the idea here is that we want to use GANs, which we did last time quite extensively, and you had a really good article where you could do your own GANs at home that would outperform what we did. So the next thing is the style transfer and all sorts of tasks which are even like a next level to what you can do with GANs. So first of all, the things we did last time, they would be useful for example, that you want to generate your data set. So for example, or generate some kind of creative content. That would be also some case. But in these cases, what we will look now, the domain transfer, networks and the style transfer is where you have some kind of source of data and you want to create something else which would be meaningful. So for example, if you would have sensory data from robot and you would like to transform data into some format which would be realistic, that would be used later for actually training other models. So I just realized that I should look up, there were Tesla Autonomy Day, where they demonstrated their style transfer models. Just a second. Autonomy Day, the realistic simulation. I think hopefully you saw that already yourself, but I will try to look up these images. Just a second. I kind of forgot to prepare that beforehand. So they have like a game engine, right? And they apply these GAN models to create from the game engine output something which would resemble what you would get from actual camera feed. So simulation rendering, neural rendering, test autopilot, right, that is what we need. Neural rendering, just a second, I will drop in images as soon as I will find some good images. Okay, I guess they have only videos, but maybe I can use videos. So let me see, can I share some video feed? Oh yeah. Trying to understand So where is the, okay, so this is not really good image, but oh man, they definitely, I remember really good examples of that. So if somebody knows what I'm talking about, you can share this, or maybe I will just drop it a little bit later. No, like I don't know why I cannot find it immediately, but there are, like, I think also NVIDIA now now have this this kind of this neural rendering option for ray tracing and all sorts of things, where you can have the actual input and then process it and get out something which would be super realistic. And by the way, there is also a few caveats to that. Actually, I found one image here. So is that, yeah, like if you would like to use this in computer games, as far as, so in the, what was here? So on the right side, I think, so it's really hard to tell myself. So on one side there was like the synthetic image, another one was the real image, like after the rendering. So I think on the right side that is after the rendering. So, but the idea is that the actual computer gamers, they didn't like to have too realistic visuals. So that is something that I read somewhere. And but it's really good for other purposes, like if you want to evaluate your models on like real life data which you don't have, then you can apply these kind of domain transfer techniques. Of course, you know, there are a lot of other applications like cartoonization filters, like there are like also all sorts of Instagram, TikTok, whatever filters, so you can add to the images, and they would also probably work using GAN techniques. So today we're going to look at one of the first ones which were in this field, which is this domain transfer network. So maybe I should fix this a little bit. Transfer network, GAN, and it works by having something which we already used in the autoencoders when we learned about that, and also in deep metric learning, so that you have the F here. So this is the encoder. So an encoder produces some kind of Z vector here, which is the same as for the normal GANs. Then we have generator, which produce the fake image, basically. So that's one. Then we are passing through the encoder and decoder or generator the two different domain images. So we have the source domain and target domain. So and then the goal is to have some kind of mix between the source and target domain, which would be then the final product. And for the production, we would use only this part, basically. No, sorry, for production we will use also the encoder part, right? So that is that, and then there is also the here on this side the discriminator, and discriminator tries to discriminate three things. Actually, you see there are three arrows here. So let me see in the chat if there is no questions. So yeah, there's three arrows. So first of all, it tries to discriminate that, detect that this image is from the source domain, from the target domain, which is not displayed really nicely here, but from the target domain, or this is actually real, or so yeah, or this is real image from the target domain. So you have either encoding. So discriminator does the following. So either encodes this target domain, goes here, 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 goes there. Either it goes from the source domain, it goes like that, or it goes directly from the source to discriminator. So there are three paths, and how you deal with three paths. So either you would have, I don't know, like three discriminators, or you can have just one discriminator with a softmax at the end. So that is what, at least as far as I understand from the paper, what they did. So they added the softmax at the end, so they have not only a binary classification, but you have 3 classes that you want to classify. So that is your discriminator here. Then you also have this really interesting thing which tries to maintain the similarity between the input source and the generated output here, so from this encoder. So you see that encoder here is exactly the same as this encoder. So and this distance, what they measure here, it could be cosine distance, it could be just L2 distance, it can be any kind of distance, and they try to measure the distance between the z vectors, between this generated z vector and regenerated z vector from the fake image. So you pass the fake image again to the f, and then you get the z vector and you try to measure that distance. So that's another path. And the last path here is the, so from the source, from the target domain to the generated image, so that it would be just like an autoencoder loss, reconstruction loss here. I'm not sure why they call it TID. What was the reasoning for that? Just let me look it up. But that is reconstruction loss, actually. We will look a few other things what they have there. I will post some images from that as well, just a second, from that paper, which I already shared. Why they call it TID? So, okay, so that's target identity loss. So really strange notion. But basically also there is in the equations really something confusing, because they use here G, which describes both of these things together. So it seems like that, not sure why would they do that, but basically that describes both of them together. So that's a generator part, that's a discriminator part. So anyways, so let's keep digging into equations and also to the more details. So I will post, okay, before we do that, let me just post a few things from that paper, what you can do with these models. So first of all, they show that you can do the style, like the domain transfer or the style transfer for 2 different dataset tasks. It's actually also not completely fair, I think, from these images what they show here, but also I think they are doing actually some smart things. So first of all, here these look really nice, these comparisons, like where you have the actual face and then the cartoon representation. But what they actually do is that before feeding to the encoder, they apply some filters to this image. So well, the end result looks amazing, but the process how you get there, it's not just directly from this to this. There is a few other extra steps, but still, it's if the end result is great and you're getting that by using GAN, that's still great. So it's just to be aware that I think as far as I saw in some of the paper notes that they actually apply some filters before feeding into encoder. So that's one. Then also this one is really nice example. So they are using MNIST. So we are using extended MNIST. Today we will try to do the style transfer for fonts. We will try to transfer style from the MNIST dataset to the Arial font. And here in this case, these are just you know, like the house number letters. So that was the dataset called SVHN, and you can transfer it to actually these images, handwritten images. So that's really cool experiment, and this is of course also very good. So that part, what I did, is there anything else? Can we move to the loss functions? Okay, let's move to the loss functions. So for the loss functions, at least I found one really strange and funny thing there, but so that will not have a problem. So this paper is actually written by Facebook Research 2016, as far as I understand. And so they're quite high-profile researchers, and that's why it's especially very strange what you will see just in a second. But anyways, the concept itself, the idea is really good, I think. So here, what we have, these are the loss functions which you're going to implement today. So it actually there is one more extra thing. So all of this part, all of these guys, they write in their paper. Actually, also the LTV in the bottom part, but which is not useful at all. So these are the LG. So these are L generator. Remember that we have two opposing forces. We have the discriminator fighting generator. So we cannot just try to optimize this without any consideration altogether. Like we cannot just string all of this stuff together and expect that this will work. There should be two major divisions in regards of the training parameters. So when we are training the discriminator, this guy, we are locking weights for all of these things. We don't want to train them. And when we are training generator, then we are locking discriminator. If you don't do this, then nothing will be learned at all. So basically, that's why there are two parts. So the discriminator part here, let me decode step by step. So we have the softmax and the cross entropy, right? So here, if you look at these small stuff here, maybe it's even too small to read. I need to make it larger, probably. Okay, so then I also need to add more this stuff. So this is the generator. Anyway, so here there is S. So it means that this is the sampling from source. So maybe I should also add here. So this is S, and this is the target. So this is the target, S and T. So we are sampling from source, or not sampling, basically just getting batch from source. Then we are passing it through the encoder, passing it through the generator, passing it through the decoder. And then we have this strange notion of 1, which means that class number 1 will be for the identification of the source. So we are saying if the class number 1 is 100%, then it means that this is actually the source input. Then for the target input, we have the same procedure. Basically, only the X now comes from T, from this part, and it has the index of 2. So it means that this is the class number 2, this is the target. So we are predicting the probability distribution over 3 classes for discriminator, the source, target, and real. So basically it's not really source target. So this is a source fake. Then the second class would be for the source target, for target fake, sorry, target fake. And the next one is just the target real, basically. So if this would be a typical discriminator, then it would have only the real versus fake. So they added extra extra classes for this discriminator. It probably would be possible to add also the source real. I'm not sure if that would help. Probably did not help. That's why they just left only these 3 classes. So that is what we have here. Then for the L-GAN-G, so this is like, again, typical generator loss, but again with extra classes. So here we have then, we're trying to have the inverse effect. So we're trying to fool the discriminator. So here in this case, the source fake is labeled as target real, and here the target fake is labeled again as target real. So this thing is trying to fool the discriminator by feeding in samples which look like target real. So that's one. But if we would just left it as that, then we would get outside only images like these. So we will not get any like images that look between those two. So to get them looking in between those two, the most important part here is L-const, which is again very strange notion of const, but basically this is some kind of content loss. So here you have the encoder of X source, and then there is a source fake, which is again encoded into encoder. And then this is D. The D is just L2, or mean square error. So D function, D of, let's call it D of U equals the mean square error of U, or L2, L1, cosine, or whatever kind of distance. So, and also this D2 here, they denoted it by 2, but it can be either the same or different distance metric. So again, this is very similar to what we already looked at before. So these are the like distance metrics, so deep metric learning related stuff, where you have some kind of metric where we measure how similar are the z vectors. So this is for that part, and here this is the most simplest thing. This is just the reconstruction loss. So this is reconstruction. I'm not sure that we actually need reconstruction here. I think like one of the reasons why you would want to use GANs is to avoid reconstruction losses, but they added here. So maybe next time we will look at cycle GAN. This will work a little bit different. So that is that. So, and then here there is the last thing, which is which is included in LG, which is LTV, which is just how would I call it, anisotropy variational loss, which is, if you look at the equation, it is trying to smooth the image. It is trying to smooth the adjacent pixels to the same value. So, and the funny thing, later in the paper, let me know where exactly was it, they say that they tried to use that LTV loss with different values, and then they decided to leave it at 0. So it's a kind of, but it's like a scientific paper basically, and it's really strange that they managed to publish this stuff even though they don't use it. Okay, I have something with my mouse. We'll try to find that line quickly. Okay, I actually found also one place where they say that they do use it with very, very small value, but I think there was at least one part where I found it where they say that they don't use it. I guess that's why they managed to publish it. Yeah, I guess that they use the LTV loss for the face part of the task. So here there is from page number 6. So they say that we will also use those hyperparameters. So they say that they use alpha and beta. So they add alpha and beta in front of those loss parts. They use it as 15, and then gamma, which is for the LTV, they use it as 0. And let me just quickly point to the full equation here. So the full equation is this thing. Maybe I should have added it before. So where they have chained together all of those guys which I just showed you. So there is the LG is L-gang plus alpha times L-const plus beta times LTD plus gamma times LTV. And they say that for the character task, they didn't need LTV. So yeah, so then in our task, we also will not use LTV. Okay, so that's it so far for the paper. Really hope that this is clear. If something is not clear, then write in the chat, and now we're gonna code this this thing, and hopefully it will be even more clearer when you're trying to implement it fully. So now let me share the code. So the template now contains of few things. So first of all, up here, so there is the characters include. So this means which types of characters do you want to include. You can add here Z, V, and so on, like 0, 9, whatever. So you can add more characters if you want to train it with like a different more characters. So the task is to transfer from the written characters to the font characters. So that would be style transfer. So there is the what samples per class. Then also there is debug, which is now enabled. If you have GPU and you want to train the full model, then set it to false. So that part then samples per class, maybe that's fine. What else we have there? So how many discriminator n passes I want? Maybe let's put it initially by 1. I had it by 2, so maybe put it to 1. I just realized that it was. So if the discriminator is, sometimes it's better to get realistic images to pass it more times. So that's why it was there. Then we have the dataset extended NIST, which we had, and then we have dataset Arial, which is dataset from font. So I'm loading the dataset from font. So there is different sizes of the letters. So there is a range of how big are the letters. Then there's also the rotation of the letters as well included in that dataset. So that is that. Then there is a filtering by the letters the characters include. And we also hashed the indexes. So I find the characters that I like to include and then save the indexes of those characters so that I can next time just quickly load a subset of dataset. So then we have 2 datasets. Oh, I see. Ah, man. Thank you, Pauls. So good that you're here. Nobody told me, so I will need to explain again. Yeah, I did not share the screen. Thank you. Wow, man. Oh, thank you, Pauls. So let me go again. So this is the template. I will also share the template again, maybe here in the show notes. Where is the image? I was talking and not showing anything again. So, okay, so we have the parameters. So characters include, which means what kind of letters or numbers I want to include in my generation of the images. So just again to show you what I mean by that, let me run it. You can also run it first time. It will download the dataset. Oh, no. So now it's just spilling out a lot of stuff here. So anyways, let me show what it is. So I have the upper side. I have the source, and the lower side I have the Arial font, which is in different sizes and different angles. So that is what we have there. And now I'm just selected ABC letters. So you see that in both datasets we have only ABC letters. If I would like to have more variation of samples than classes, then I will just type in the chars include more stuff there. So I'm just dropping on Jamboard that example as well. So this is the characters include. Then how many samples, then learning rate, the Z size, the embedding size. I don't know, like 128 is a pretty big size. Maybe 64 would also work. Then discriminator n, which I just said that I forgot to left it as 2, but I think it should be 1 because I think discriminator is too powerful in this task. Then the coefficients alpha, coefficients beta, which was in the paper 15, as they say. What is this? I don't know. Too long, don't know. Anyway, then the bug. So if you have GPU, then if you want to train it fully, then you should set it to false, or just pass it as false. I also have run path. So if I pass run path as some kind of text here, it will create a folder and save the plots, not show them. So that's also a really nice way to train final model. So that part. Then let's go down here. There is the MNIST dataset. There is the Arial dataset. Arial dataset is just a font with different sizes and rotations. Then there is the filter dataset where we filter them by characters which are included. So if I include A, B, C, D, so on, I want to save those indexes so that I don't need to go over the whole dataset every time and find those indexes. That's why I'm using this hashing and saving and then loading, and then I get the subset here. Subset is, so this way is really recommended way to generate all sorts of combinations of the datasets. You should not do this beforehand. You should just use the indexes. So there is the torch-utils data subset, torch-utils data concat set or something like that. So those ways are better than just making this in code beforehand, because otherwise you can mess up something there, and then just from experience, it's better to have index selection from the datasets than just modifying them directly in the classes. I found I had a lot of issues with that in the past. So yeah, so then I generate two datasets. I check what is their length. I generate I make two data loaders. And then we have three different models. So one is model E, model encoder. So it was in the equations model F. So in equations, this is Fx, but in reality, normally people call them encoders. So then the encoder should produce something, in size of batch, z size. Then we have the decoder. Oh, sorry, not decoder. D is discriminator. Maybe I should call it different. So this is discriminator. So it is kind of like a classifier. It tries to classify, is this image a real or fake, or from one domain or from other domain. And it generates output as batch, 3, which is the probability distribution over 3 classes, which is the fake source, fake target, and real target, I think. Yeah. And then the G. So the G is generator, and this takes the input. This takes the Z size. Where is the Z size? Here, the Z size, and scales it up by having the. In this case, it does it by upsampling once, upsampling twice, and then just applying some convolutions, and then at the end sigmoid, because it's from the range from 0 to 1. So then we have three models: encoder, which encodes the image into Z vector, the discriminator, which detects if this image is a fake, and generator, which that generates from Z vector to fake image, basically the output. Then I have the parameter count code, because that is again important. If you don't have enough parameters, like I would say like hundreds of thousands, then most likely it will not work. Then this is also super important lines. So there is the optimizer for D and optimizer for G. So of course there is option to use one optimizer, but it's also a little bit dangerous that sometimes maybe some gradient is not detached properly. So I'm using it doubly safe. So first of all, I'm adding two optimizers, and there is also additional benefit of this, because if I detect that discriminator is too powerful, I can just reduce the learning size, learning rate for discriminator, for example. I could add like, I don't know, like twice as small learning rate for discriminator if I detect that it's too powerful. So that's again additional bonus. But you could do this all in one. So, and here we have the parameters for discriminator and parameters for generator and encoder here. Then I have all of my metrics. Then I have my main training loop. In main training loop, there are a few interesting things which are different from previous tasks. First of all, we have the just going through the data source, data loader source, and data loader target. So we're getting XS, which is X image from source, and X image from target. And we also need to do this simultaneously. So that's why I create iterator here, and then I call next here. And what will happen is following. So when the shortest data set will reach the end, basically, in this case, there's definitely that target data set is smaller than source data set. It will raise exception stop iteration, and that exception will be catched not probably, but it will be catched by the iterator of source, and it will exit this loop. So that's why it works. But in case if this will be larger than the other one, it will also work, because then it will just not complete the whole loop and will create the next iterator here. So if you don't understand the iterators, next functions, and the stop iteration exception, you should look again a little bit more regarding how the Python works with regards to iterators. So that is really useful way to have, for example, 2 simultaneous batches generated at the same time. So this is the way it's done. Then we have break just for illustration. So I will delete the break here. And we need to implement all losses. And there's 2 parts, basically, because so we could do this just in one pass. There is no problem to do this in one pass, but there is a problem in sense of if I would do this just in one pass, then my discriminator and generator will have the same x and xt. That is not beneficial, because they will be in 2 direct conflict. If I have different x's and xc and xt, they will converge better. So it's the same idea as having a z vector, the same z vector for the generator and discriminator. It's better to sample z again here and again here, not to have the same. So that's why I have this small code of n0, and then for the n where it's larger than for the discriminator. So in this case, if I just also want to double check that I didn't mess up this as well. So n, so if I have n0, then there will be n1, then the n1 right. I think I messed it up. So anyway, so I think you should have here like that. So because otherwise the discriminator is again too powerful, it has too many iterations. So it will mean that if I had n there, then there will be n1, and the n1 should be then equal like that. So there is a small change here. Please do that as well. Yeah, and change this also to the number 1 basically, so that we have only 1 iteration for the discriminator. Okay, anyway. Yep, so I will add this to the Jamboard so you know. And now we're going to start code this stuff. I think it will not take too long, hopefully. Hopefully we'll get also nice results. And here, by the way, now there is the XS, the source, and X target, but we will change this to the generated output here later. Okay, so that part is done. Okay, so let's start by adding those endings of the model. So here the model E, the model encoder, so this is encoder, it should generate the output of size batch comma size. So if you look here in these equations, so in this line the out channels is 64, num features 64, then max pool does not change the features, adaptive pool does not change the features. Oh man, this was the thing which I thought is strange. Yeah, I forgot. Okay, so let's add here some additional stuff that doesn't make sense. Adaptive on max pool 1 by 1. So this is the reduction. This is the reduction. I forgot to add one more layer here. Yeah, please add one more layer here. So from 64 to 64, num features, relu, I think it will be fine. Yeah, so just add these two, copy these two lines here. I will also add this to Jamboard. So, because it doesn't make sense having max pool and adaptive max pool just one by one. It just doesn't make sense. So anyway, so we'll add here torch and then linear, and there will be in features of 64 and out features of z size. Right, so that's what we need. Then also, I don't want this to be flying into infinity, the z vector. So if I'm sampling z vector from the Gaussian distribution with the mean of 0 and standard deviation of 1, then I would get something in the range from -3 to 3 in most cases. But in this case, it will be just unbounded. So to have it L1 bounded, I could add the torch and n tan h. So this would make sure that my z vector is always in range from -1 till 1. So it will be 128 dimensional embedding with the range of the L1 space. So it will be kind of box space in the embedding space. Of course, you can easily create it as the spherical space by applying the L2 norm or something else. So we already talked about that part. Okay, so I will add these equations to the Jamboard. There are very few lines needed to add. So this will be on slide number 5. Great, that is added. Then the discriminator. Okay, this is again interesting part. Oh no, again I need those lines. So please copy again these 3 lines of additional layer, which I forgot here. Because again, it doesn't make sense, max pool and adaptive pool in a row. So those 2 lines there, and then again, very similar output, but different logic here. So torch and then linear in features 64, out features, not 64, out features will be 3. So we have 3 classes. So we are trying to discriminate between following. So 0 class means this will be the fake source. 1 will mean fake target, and 3 will mean real, basically, real target. So this is what it will mean, those 3 probabilities. And if I have 3 probabilities, then what should I add the last layer? Maybe I should ask this in chat. If this is probability distribution, what should be last layer? My question in the chat. And so these are now logits. And if I write my own loss function using just torch logarithm, then what should be the last layer here, if this is a probability distribution? So now this unbounded, because now, if I pass it to MLP, I can get numbers like something like, I don't know, like this, or mean minus something like that. So this doesn't look like probability distribution if this is my output now. So what should I add there? I think you should know this really easily. This is my question in the chat. Do we have any answers? Let's wait. Softmax, of course, Paul's is got 100% in my course before. And Pulse, of course, is really smart guy, and this is cookie for Pulse again. So, by the way, Pulse is not even finished bachelor degree, but even though the other guys right here are the master's program. So anyway, so this is good. So this should be softmax because this is a probability distribution. Softmax, and here we'll have dimension of -1, right? So that's a good job. So we're adding that part, dropping this to the also to the Jamboard, where we need to add a few things here. We're closing into the loss function. Not much done. I think actually the next thing will be the loss function. I don't think we need to work more on the models. So this is done. Then here, this is already done. The generator, it generates 20. It generates one. So basically, what it generates, let me show you. So it generates the batch, 128 images. If you would like to generate some kind of other deep fakes, like or Putin speaking or something else, so then you change all sorts of dimensions here for the images. So this part, fine. So now we are ending in with the loss functions. So these are the loss functions. I forgot to understand. So yeah, so all of these style transfer methods can be also used for all sorts of deepfake generation from audio, video, images, all sorts of things. So anyway, okay, so yeah. So first of all, let's work with the generator part. I know that usually people first start with Discriminator, but in this case, there is the just to avoid all sorts of problems with the gradient parameters. I like to start with generator, but it doesn't matter because just the first step of first batch. So here, let's start then. Let's write the first z vectors. So z from source will be from model encoder forward x of s. So this will be the embedding for the source domain images. Then embedding for the target domain. Then, because the discriminator will also have a y output, so let's call, in this case, the, let's call it g, so this will be the generated output, gs model, g from forward, zs, so from the embedding of the source. Then from the, what else we need here? From the embedding of the target, we will generate target. Then there is the additional thing which is needed in the const loss. So this will be then kind of z embedding got from the zs. So zzs really, so this is like a cyclic kind of thing. So again, you call it yourself. So here, model e forward, and to get this, we should call gs here. So it means that it's kind of, it's getting it, so the embedding from itself, basically. So you're feeding in here. So here you're feeding in xs, you get zs, then you feed in zs into generator, you get gs, and then you feed it back into encoder again, and you get zzs. So in this case, there is a chance that might be necessary to detach some gradient here. But it also could work just by passing a gradient from both sides. Not really sure at this moment. You could play around by detaching it, for example, here, or maybe before that. But let's leave it as that. If it will not work, then we can start playing around here. So let's write here might help detach detach gradient somewhere. It's just because it will be in the both sides of the loss function. It might work, it might not work as well, so we'll see if it works. So, okay, so that is that part. Then we also need two discriminator outputs. So to get to discriminator outputs, I prefer to ensure that discriminators do not accumulate gradients, even though it's most likely that they will not accumulate because there are two optimizers, but still, I just want to make sure that there is nothing happening there. So model D, model D parameters, and let's set that I don't want to learn parameters here, requires grad false. I just want to learn generator related things. I don't want to touch discriminator here. So that is why I'm doing this. So then Y of GS, so this will be then model D forward of GS, and then again Y of GT. Again, this can be optimized by, for example, adding those two things in the stack as a batch, but also there is at least in the GAN hacks article, which I shared you last time, they say that it's better not to mix in the same batch the fake and real images or from different domains. It's better to have batches independent. Maybe also it's better to have the backward pass independent, but right now let's keep it just the batches independent. So it's definitely for the batch norm better. So that part is done. Okay, so then let's start to write the equations which you had written in the having the Jamboard. Jamboard. So loss gang. It's already below here. So I will start by loss gang. So this will be then minus torch mean of first thing first. So the first thing is then the torch logarithm of D Okay, I have some kind of siren going on in the background. Just a second. Okay, I guess you also hear the sirens. It seems like that there is some kind of testing of the sirens also all around the Latvia, I think. Maybe you can write in the chat if you can also hear those where you are located. I was a little bit worried 1 minute. Okay, so hopefully that will end soon. Okay, so there is the unexpected surprise. So, okay, so this will be first logarithm part. This will be from the y of generated s, and this will say that the two, this will try to fake that the target is real. So this will try to make sure that the generated source is kind of, it looks more like a real image. So and then let's add here epsilon just for stability. So this is 1. So again, just to remind you, so model D outputs is the 0 is 0 is fake source, 1 equals fake target, and 2 equals real target. So like that. And here here I'm actually feeding in the fake source, which should be 0, but I'm saying that this is 2. So I'm saying that something which is not correct. So I'm saying basically opposite to what is reality, so that the generator would be so good that it fools the discriminator. So that's why this is so not like in reality there should be now 0, but I'm saying this is a 2 because this is generator loss. So this is that part. Then the second part is minus again this thing, but then the target. So the target also should look like the real image. So that is good. So then the constant loss, which is then even more simpler. So this is torch mean of D. So the constant is torch mean of, oh sorry, this is not the simplest one. This is actually important one. This is the distance between the embeddings. So this is then from this source, Z source minus ZZ source, ZZ source squared. So this will be L2, but it could be also cosine distance, or L1, or I don't know, like any kind of distance which you like. So the KL, PLDA, all sorts of. So here then this TID. So this is the actually reconstruction loss. So reconstruction loss. In my opinion, this should not be that powerful. Reconstruction. Maybe if the images would look so they would not match the correct classes, then this should be then changed. I just realized that my generator, my data source also does not match classes. Okay, but that's fine, because we will use, okay, I know, everything is fine. So because it will, for the visualization, we will use XS and then generated T, which should match the visual representations. So here this will be then the XT versus GT. So this is reconstruction, and finally we just need to multiply everything together. So this will be then loss GAN plus alpha, coefficient alpha, loss constant, plus coefficient beta, loss TID. Okay, cool. So this should be done. I hope I don't have bugs there, but this is generator part of the loss. Those are the red equations on the slide number 2. So I am dropping this to the Jamboard slide number 6. And then the last part is the discriminator. So again, I think we can copy part of these equations. So again, we need to rerun the X generations, so these things. So I'm running these things again. I also want to run these things again, but so basically we can copy almost everything up till there. Only now we want to enable gradients. Enable gradients here. So we enable gradients. I hope everything is fine now. Okay, we enable gradients, then there's only one extra line necessary, which is the YT, so real target. So from the XT. So this is the kind of really important source of information for the loss function. So it's saying that I want that my generated output looks so that is not that it looks, but I want to be able to detect that generated output is real or fake. And this is the main purpose for Discriminator, but generator will try to fool this purpose. So this one line is very important. Okay, now we need to write again the loss functions with the logarithms. Again, just to make it simpler, we can even copy those lines from above. We need to just change this to the D, Discriminator. And here we need to change a few other things. So first of all, this one should be 0 because we are trying to detect that this is a fake source. Then, if I press enter, just a new line here. So the next one is we are trying to detect that this is a fake target, 1. And finally, we are trying to detect that the last one, XT, is actually what we want, the real, like that. There is also one extra thing which I, again, forgot, is that we need to detach some things. So here, let's write detach. And here as well, detach. So let's write here that these gradients should be detached. Gradients not flowing through generator. So that's about it here. I think that's about everything we need to try to train it. So this is Discriminator loss. Maybe I made some mistake, but I hope I did not. Then the last thing which should be added is at the end for the grid, what we generate the image, we should display not XT but the generated source. So generated source I want to display. So from the X source I want to display generated source. So that is the last thing which need to be changed as far as I know. So I will add this to the slide number 7. Where is my image? Okay, so I added that as well. Okay, now I scroll back to this part of Discriminator so you can follow it up, and if you have any questions, write in the chat. And meanwhile, I will try to run the training procedure. So, live. We'll see if we need to fine-tune something. Right. Remember, if you want to train the full model, then you need to also say, is the bug false? Is the bug false? Let me see. Scroll up, 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 up. Is the bug true? This should be, is the bug false then? Is the bug false? Maybe I should definitely display that as well. So if you want to run the full model, I mean the full dataset training, then you should set it as false. Now let's scroll back to the Discriminator. So this is the Discriminator. Again, this is exactly the same equation as we already had. Okay, so we're starting the training, looking at the losses. will share you some images as soon as I will get some results. As from previous experience, I think that there is two dangers. I think one danger is that Discriminator can be too powerful. Another danger is that we could get the mode collapse, which because we are actually also not using now Wasserstein loss, but we are using just cross entropy. And it seems like that I'm getting mode collapse. I will show you. We'll try to make then Discriminator weaker probably. Okay, I will show you what I get as soon as I will get something meaningful. I have 42 epochs. Okay, let me share something. 46 epochs. At least so that you know that something is happening. We'll start sharing stuff on the Jamboard. Slide number 8. So this is how it looks like after 46 epochs. We'll try to, so you already see that the Discriminator is pretty much dominating, and it's destroyed the generator most likely. Maybe it will come back, so that's why I'm not just yet stopping and just a little bit waiting. Maybe there will be the flip back, but it's quite unlikely actually. And the other thing which you can already observe is that all of the images look about like the same. So that if they look the same, then it basically means that we get a mode collapse, which means that we get all of the, or maybe there is some bug. So let me check also. GS. I don't think that that's a bug. I think it's collapsed. So to get out of the mode collapse, which means that it produces the same image for all of the inputs, it's really hard. I don't think it will happen by itself. So probably I will need to reduce the power of like the influence of the Discriminator. Nonetheless, I just want to train it fully. Okay, so what I will do, I will create, meanwhile, while this is training, I will also create another parameter. You can hard code it if you want as well, but what I will do, I will add here learning rate D and learning rate G. So I want to have the D learned like 3 times slower. So this will be like that, and then I will write, where do I have learning rate, Rx learning rate. I don't want this anymore. You can just hard code it here if you want. Rx learning rate D, learning rate G. Hopefully now it should help. So this is what I'm running here. Let's see. I will share with you some results as soon as I get them. So this is B3, this is running, B4. This will be diff learning rates. Make sure that I upload everything what I need. This is different learning rates. data sets are also quite small, so I'm just using 2,600 samples from each of the data sets. Like larger data sets will definitely help as well. So different learning rates, we'll see if that helps. Meanwhile, I will update you what I get from that first run. So I'm starting to get really interesting results, but those results are quite like jumpy. So it's definitely clear mode collapse. I think last time we talked about mode collapse, but I did not actually demonstrate you mode collapse. And now you're getting clear mode collapse. So here what's happening on the first run, which I tried. So now it's generating something resembling a letter, like from the font A letter, but it's generating it from all of the samples. So that's definitely not great. So one option actually is to not only change the discriminator learning rate, but also to increase the importance of the L-const. Plus also maybe we could detach it from somewhere. Yeah, definitely. I suggest add one more thing. So I've run also the experiments with different learning rates, but I think we need to detach it here as well. So I think it might help here. Detach. So detaching GS from the ZZS. Oh, sorry, I did not share the screen. So in this line, ZZS detach GS, and if it will help, I will definitely also update that in the notes. So I'll try to run this again. So in parallel, so this will be a new run. This will be detach GS. Hopefully this will help as well. So different learning rates, what is getting that? There's still mode collapse happening. And the loss plot, still quite a lot of significance towards Okay, by the way, I need to look at the raw numbers as well. So what we get from the raw numbers, so the loss G is 11, loss D is 1. From the loss G, loss gang is the most important one. Yeah, it seems that the loss const, so the const, that argument should be probably improved. Basically, those two last coefficients maybe should be even larger. Okay, so let me see the new run. Detaching. I don't see like huge difference, probably because the coefficients are too small still. So okay, I'm starting to post these changes to the Jamboard as well. So one is to add detach here. Okay, so it'll be interesting to see how far we get in a few minutes. So this thing is detached. Then also let's play with coefficients. So these are still way too little. Well, let's try to like put it to 50. So 50 alpha, 50 beta. Okay, let's see if that helps. So running this as 50, 50 alpha, beta. So we have now something happening. Oh no, accidentally. Okay. Seems like that it does not help a lot. Maybe it just needs to train longer. I don't want to wait so long. Seems like about 100 or so, it starts to converge, starts to get something reasonable about like 100 epochs. But then it's still, there is this mode collapse problem. We'll share those things as soon as I get something. Maybe I just need to train them longer. I see that with larger 50 coefficient of those alpha and beta, I get a much more interesting loss plot, so I will share that definitely also in a minute. I'm getting that there is some kind of action happening in the part of the L const. It's fluctuating a lot more, and definitely that will also help. If I'm not getting these results like in, I don't know, the next 10 minutes, then I will just pause them a little bit later. But it should be possible to converge, not to converge, but at least to get something more resembling the output what we need. There is also an additional few things which I would add. Maybe the original researchers also were doing this. So is that here, on the, where is the generator loss? So yeah, so ZS, so this is the difference between the source, Z, oh, that's interesting comment, really interesting. Gin saying that he is getting something resembling A and C, but it's not stable. So yeah, as you know from the last time when I shared the GAN hacks, there's the stability is not one of the features for the GANs. GANs have really nice other features like having the beautiful results, you know, when they are not directly related to the loss prior functions. But stability is not one of the features. The other thing is that this could be definitely improved by adding Wasserstein loss. So I mean, like if we would not have the maybe it even could be possible to add Wasserstein for the 3 probability distributions, which should definitely also work in my opinion. But if it will not work, then you could just create 3 different discriminators and apply the Wasserstein loss, so that should also help. Maybe larger batch size also should help, because now I've actually just realized that I'm using very small batch size. So my batch size right now is 64. Let's make it, well, I don't know, like 256. I will try to run it again somewhere. Okay, so this will be then new run, batch 256. By the way, GINT, if you get some nice outputs, at least somewhat resembling what we need here, you can share maybe somewhere the link of the image. That would be great. I will put that also on the slides. This is very similar to way how you would work with reinforcement learning, where you just run like hundreds of or thousands of experiments and always expect really good results, and it's not that easy to predict when, like, what exactly would work. Probably would need to have proper grid search to search over all of the parameters which are affecting all of this stuff, and but then again there will be the new problem, because if you are researching GANs, you know that there is the metrics to measure how good is your result. So one metric is inception score. There is also a few other metrics, and basically there's this active research how to measure how good is the output of your result. I think in that paper which I just referred, they used pre-trained VGG Z vectors as their kind of like measurement of how good are the results. Now with 256 batch size, At least with 256 batch size, I see that I'm getting the somewhat fluctuate. Like it, at least I got for one moment fluctuation in the what is this, in the generator loss, I guess. Yeah, generator loss. So it was not only growing up. Maybe the learning rate is too high, because the batch size and learning rate is two parameters which are very connected. When you increase the batch size, you definitely need to increase the learning rate as well. But now, if the results are better with larger learning rate, with larger batch size, it might mean that learning rate was too high. Okay, this is this. Yeah, definitely with this small batch size, this is not working very well. Okay, I will try to increase even more the batch size. So let's say 512. Oh, right, the num of epochs, there's something strange, why it's not respecting that. Yeah, I forgot to implement, I guess, that part. Yes, so this should be epochs. Right. And here I would like to have 1000 epochs, I don't know. Maybe 1000 epochs it would work. So this would be done like that. I will also check if my shuffling for the datasets is enabled. Yeah, shuffle is enabled. Great. So 512 batch size. Let's try again. Gambling continues. So let's see. So this is that. This is this. This will be batch 512. I promise I will not torture you too much. I just want to debug these parameters a little bit to make sure that it works, and then we will end today. And for the homework, probably I will just try to pick some paper which is not too difficult to implement, which would go in the same direction as this domain transfer GAN. Maybe some improvements in this direction, and then you could try to apply it. If by any chance, like if you try to apply it and the results are not great, then I would also give the high score. Just need to have the equations correct, because the hyperparameter, the research part, that is something which you normally do on supercomputer or on some cluster, where you just tries to run like thousands of grid searches and then grid search runs, and then just find something which works the best. Well, but now we don't have time for this. Hopefully we will get some result. At least for me right now, all of the runs that I have done gets the mode collapse. Maybe I should make even larger coefficient for the maintaining the input versus output. But batch size definitely helps. By improving larger batch sizes, make the loss plots look that the GANs are not just growing indefinitely. So definitely larger batch size should be added. I'll hopefully share some images soon. Okay. 200 epochs. We'll go over my equations again one last time if I don't have any mistake, and then yeah. So okay, I'll run it again. So this is 220 epochs. So try to change it once last time. So discriminator, fine. Z size, not sure about that, but then the alpha and beta maybe even larger. So I don't know, like we could add it to like 150. So that 512 batch size, 150 coefficients. Okay, let me check the equations last time. Here could be added also the X part. Maybe I should do that. So I could add here also XS minus GS. Another reconstruction, maybe that would help. And these guys, YT 0, 1, 2, quite straightforward. There's nothing much here. These are detached, right? Maybe just to make sure that there is nothing going on bad, I could add here also 0 grad both of them, but I really doubt that that's the reason. So I'll add that part. And I could just an experiment add here additional term. So to have the XS versus GS as well. So in any case, XS should not be actually GS. XS. Yeah, that's why they did not add it here. Source should not be then same as the output. Definitely not that. Fine. Okay, let's leave it as it is. What else we could do? Try to change maybe some metric. Okay, we could try to just use absolute values. So here torch, so L1 distances, because we also have L1 embeddings actually. Okay, let's try this one. And this will be L1. Okay, I will add some image regarding how it looks like with 512 batch size. So 512. There you can see that there is actually the initial, specifically in the beginning, there was a drop in the generator loss, and it's also nice to see that TID is actually alive, but it seems like that the const loss is too low. It doesn't change, so, but at the same time, no, it's actually the const loss is very high because it's totally related with the G. So in that case, the L, so the TID, which is the reconstruction loss, is too low. So maybe we should have some difference there. So I should try out difference there. So what I mean by that, let's try to have that the alpha is 50. I think it was alpha, the first one. Yeah, so alpha is 50 and the beta is 150, or maybe even more. So I don't know, like let's say 15 versus 150. So this will be a big difference there. So this is 50th. I guess also these kind of models are prone to the mode collapse. Ah, right, thank you. You submitted in the classroom. Thank you for communicating here, because of course I don't see sometimes things. So yeah, that is excellent. Thank you, Gintz, for sharing that you were posting that on the classroom. Did you post it in classroom? You submitted some of my results in the classroom. That's great. Maybe you submitted as a task, probably. Yeah, so that's great. Thank you, Gintz. Oh, nice. You have really nice results. I will need to check what is actually your parameters, but your loss functions are looks really nice. Yeah, definitely something what I did in my model is something different that you are doing yourself. So I definitely like Gintz results. So cookie for Gintz, that's great. Thank you very much. So I will share on the Jamboard Gintz results, and then I will later definitely need to look what is different in his parameters and my parameters. Of course, there are some problems in the results, because it seems like that Gintz results, the identification between the source and target is not matching exactly. Like if the final result should be that if I have A here, then I get A here, so that's good. But if I have C here, then I should have C here, not here for A and C here, or for A and B here. So it seems like that in this case, the either the const loss or TID loss is too weak here, but in my case, it's just like mode collapse, and that's definitely not good. I'll also take a quick look on what kind of parameters are you using, as these models are very prone to the issues with parameters. So what kind of parameters are you using? batch size 64. Okay, we'll try to replicate your parameters. So batch size 64, not the larger one. So learning rate, the same for both. Coefficients 50. Okay, let's try. What about detaching that part? Did you detach it or not? For the ZZS, you did detach, okay. Okay, great. Just a few things, and then we will end today. I will just make sure to try to run it with GINS parameters, so that's great. I think that's excellent that you got something which is not in the mode collapse, so that's good. Try to check what I have. What is the differences? Make sure that I don't have bugs. Oh, 15, okay. That was what I used in the paper as well, 15. Yeah, I don't see huge differences between the code. It's just, I guess, the parameter issue, which is pain. If it's just by the parameters, then it just means that it's very hard to find it quickly. Okay, I will try to run the last time. So 64, batch 64 test. Okay, I will run this last time and then we will end today. This is really interesting. Even with changing parameters, it's still quite the same. Just a second, I'll do the last run. So might be that that the PyTorch version is also something matters, like optimizers, for example. So I could try to use different kind of optimizer. Sometimes they recommend to use SGD for the determinant, for the discriminator, sorry. So SGD run. Or maybe I'm just too impatient because I'm looking at the examples at every like 100 epochs or so and trying to want to get sooner results. Okay, I will share some formula later, like what kind of parameters should be used to improve the results. I think that's it for today. I will prepare the homework so get some similar method. And next time we will talk about cycle GAN. And I think the next time just need to double check it will be not next week because next week there is the yeah, so you're saying at 100 epochs, yeah, that might be also a problem because I'm a little bit too impatient. So the next time seems really, so I think we can held the last kind of workshop together on 7th of January, I think. So and then you will have time to finish all of the homeworks till the end of the session in January. Maybe we will do maybe one more session, but basically I want to do cycle GAN with you together because cycle GAN is also extremely popular method for doing the